Hello, everyone. Welcome to the third lecture for Calc 3. In the first two lectures, we looked at parametric equations and what kind of information we could derive about derivatives, integrals, calculus in general, using parametric representation for curves. Next, we kind of want to shift our attention and start to look at an extremely useful coordinate system. Normally, what we're used to looking at here is Cartesian coordinates. So we know Cartesian coordinates are x and y, where x and y are both just real numbers, right? And what do Cartesian coordinates tell us? The x indicates how far away we are from the origin in the horizontal direction. Here, I'll label my axes. Right, this distance here is x, and then the y entry, or the y coordinate, tells us how far we march in the vertical direction, whether it's up or down, right? And so this point out here in red is x units away from the origin in the horizontal direction, and then y units away from the origin in the vertical direction. It gets us somewhere out here. Another extremely useful coordinate system is polar coordinates. Now, instead of polar coordinates, we want to look at a radius and an angle. And so here, really, we can talk about a negative radius, but for now, let's just introduce it as the radius being a non-negative number. We'll talk about what it means if a radius is negative in a little bit, but for now, let's say our radius is non-negative, and we always impose that theta has some sort of bound. It can have a different bound depending on a function maybe, but what we're normally going to look at is the bound between 0 and 2 pi. And how can we represent a point xy that's normally represented in Cartesian coordinates? How can we represent this as polar coordinates? Well, we take the given point that we labeled as xy, and we take its distance from the origin. We indicate how far away is a given point from the origin, and that's our radius. And then we also specify its angle, the angle that this line makes from the x-axis. We specify that angle and call it theta. So we can represent this point as how far away it is from the origin and the angle that this line makes from the x-axis, as well as being able to represent it just by how many units in the horizontal direction, how many units in the vertical direction. And so let's see how we can go back and forth between the two. So here I said, notice we get a triangle. Maybe I'll, in green here, draw this triangle we get. We can use this triangle to get some relationships between Cartesian coordinates and polar coordinates. If we look at this triangle here, we have that the hypotenuse is r. We have that the opposite edge is y, right, because it's the height. And we have that the adjacent edge is x, because that's the base of this triangle. And we also have an angle theta. Now we can use some basic trig relations to get conversion formulas to go between Cartesian and polar coordinates here. So what are a few things we know about triangles? Well, the first thing we know is the Pythagorean theorem, which says so Pythagoras tells us that x squared plus y squared is equal to r squared, right? So we get this relationship here. This tells us if we start with an x and a y, we know what the radius is going to be. So this is the first step in converting from rectangular or Cartesian to polar. Okay, so this is the first relation we have, is thanks to the Pythagorean theorem. We know that x squared plus y squared equals r squared. What else do we know here? I'll kind of copy our picture quickly. We have x, y, r, and theta, and we are converting from rectangular to polar now. And we learned that x squared plus y squared equals r squared, right? And now, what else do we know? Well, we can take a relationship with y and x and relate it to theta. Namely, if you think to the trig function tangent, tangent of theta should be opposite over adjacent. And so if we write tangent theta as opposite over adjacent, then we have the tangent of theta is y over x. So if you'd like here, we can get the following list here. We have r squared equals x squared plus y squared, and then we have theta equals arctangent of y over x. And these are our formulas now. If we start with rectangular coordinates, we can convert to polar coordinates using these formulas right here. You just plug in your x and your y, and then this gives you a formula to solve for that point in polar coordinates. Now, of course, sometimes maybe it's more convenient to represent this just as tangent theta equals y over x. I wrote it in this form to show that we can just like explicitly solve for r and explicitly solve for theta, right? But sometimes this may be a more convenient way to think about it, is just leaving it in this form. Okay, so cool. So we have these. Now, what about going from polar to rectangular? Let's say we have some polar coordinates that we don't quite understand where this point lies on the in the polar grid, or say we have some polar curve and we don't know what this curve is, how this is behaving, so we convert it to rectangular or something. So let's look at our triangle again here. Right, so all of these equations can be derived just by studying known relations with a right triangle here. So what do we know about right triangles? Well, since we've taken trig, we have a few relationships here. We know that cosine of theta is adjacent over hypotenuse, which for this triangle here is going to be the adjacent is x and the hypotenuse is r. So this means we have cosine theta equals x over r. Well, that means x equals r cosine theta. And what about sine? I'll write sine down here. Sine theta is opposite over hypotenuse. And opposite over hypotenuse is going to be y over r. Well, coming back up here, that tells me then that y is equal to r sine theta. And now we have our equations to go from polar to Cartesian or rectangular, right? You plug in an r and you plug in a theta, and it spits out your x and y values. And so we have these relatively simple formulas purely derived by knowledge of a right triangle to convert between coordinate systems. So now let's look at some examples. Let's just take some points. Say, let's take some like a polar point and express it as, or let's take a point in polar coordinates and express it in Cartesian coordinates and vice versa. so we can have an idea of how we use these formulas. Okay, so let's do, first let's convert, so let's do some examples. Whoops. So here's the first one, and this one's going to be from, let's convert the point 1, 1 to polar coordinates. Maybe I should say, let's convert the point xy equals 1, 1 to specify that we're in Cartesian coordinates. Let's convert the point xy equals 1, 1 to polar coordinates. Okay. So first off, let's kind of keep a picture in the back of our head here about what's going on. We're at the point 1, 1. So that means in the x direction and in the y direction, we march over 1 and we march up 1. And this is our point, right? This is the point xy equals 1, 1. And now we want to use this and convert to polar coordinates. So let's remember our conversion formulas. Here we had r squared equals x squared plus y squared, right? These are the conversion formulas to go from Cartesian to polar. And then we also had that tangent of theta equals y over x. So we'll keep these in the back of our mind. And let's just plug in and see what we get. We're going to get r squared equals 1 squared plus 1 squared, which is 1 plus 1, so 2. So r squared is 2, which means r is root 2. So we know then when we look at this distance from the origin, this is root 2, right? And again, because of how we derive this formula, this is just a result of the Pythagorean theorem that r is root 2, right? Because we're just using the Pythagorean theorem here to find r. And now we can use the second equation, right? Tangent of theta should be y over x. Well, it's 1 over 1, so 1. And we need to know, when is tangent of theta equal to 1? So maybe you remember from having to use the unit circle so much, or maybe you have to Google the unit circle to remember it. Totally fine. Or maybe you want to figure it out on your own. If you remember, tangent of theta is equal to 1 when theta is equal to pi over 4. So theta equals pi over 4. So that means in polar coordinates, xy equals 1, 1 can be represented by r theta equals root 2 pi over 4. Okay, so there's an example of converting from Cartesian to polar. And I want to take the time now to note that polar representations or representations of a point in polar coordinates is not necessarily unique, right? So for example, I was talking about a negative radius earlier. Let's look at what the point negative root 2. So here, I'll draw a new picture on the next page. Okay, so let's say we had our point root 2 are here. We had this point out here that was root 2 pi over 4, right? We can get a representation of this. We could also represent this point. So here was our angle, pi over 4. We could also get the point root 2 7 pi over 4 to represent the same point. Because what is the angle 7 pi over 4? Well, sorry, 9 pi over 4, because we want to go all the way around and back to this point, right? And 8 pi over 4 would be 2 pi, which would give you one complete circle. But we want to go pi over 4 past that. So it would be 9 pi over 4. And so if you broaden your bound for theta, like say it's not bounded by 2 pi, but bounded by 4 pi, then you get the same representation of this point here, right? Another way we could represent this point is if we were to look at the following angle. I'll try to draw it in green, to where it's completely opposite of pi over 4. And this should be, the green angle here is theta equals 5 pi over 4. But this is in the opposite direction. And you can indicate the same point by using a negative radius. So this is the same point as negative root 2, comma, 5 pi over 4. See, because if you're at the angle 5 pi over 4, you're in the opposite direction as pi over 4, but now we're taking a negative radius. So you go, instead of going in this direction, as we would with a positive radius, with the negative root 2, you go the same magnitude, but in the opposite direction. So it gets you to the same point here. And so this was just kind of a side note to remind us that polar coordinates, or to show us that polar coordinate representation is not necessarily unique. Okay, next let's do an example of going from polar to rectangular. So let's do this one here. So let's convert the point r theta equals 6 negative 5 pi over 6 to Cartesian. I kind of use Cartesian and rectangular interchangeably here. All right. In my studies, I study geometry quite a lot, and which basically means I'm a very visual learner. I learn math a lot better when it's pictured, and I think pictures are very helpful, especially in Calculus 3. It's easier to understand which method to take once you kind of see the picture, at least for me anyway. So with that being said, let's draw a picture first. So let's find out where the angle negative 5 pi over 6 lands us, right? So negative pi would still land us along the negative x-axis, right? Because if you go pi this way, negative pi is 180 degrees in the opposite direction, but they still get you to the same place, right? So negative 5 pi over 6 means we stopped pi over 6 radians short of the negative x-axis. So this angle in blue is negative 5 pi over 6. And we know that r is 6, so this distance is 6, and we're out here in the lower left quadrant somewhere. So this is where our point is. So we should expect that after we convert, our x value and y value are both negative, right? So let's remind ourselves of the conversions here. To convert from polar to Cartesian, we have x equals r cosine theta and y equals r sine theta. Okay, and now we just need to plug these in. So x equals 6, because r is 6, times cosine of negative 5 pi over 6, which, again, So cosine of negative 5 pi over 6, you may notice this is the same as cosine, like in the other direction. I'll draw it in green here. It's the same as 7 pi over 6. So if you'd like, or if you have the unit circle memorized or something like that, then this would be the same as 6 cosine 7 pi over 6, which may help you remember that this is 6 times root 3 over 2. Sorry, negative root 3 over 2, right? Because it's on the left side of, or it's on the negative x-axis. So this means we have an x value of negative 3 root 3. All right, and so now let's look at the y value. We get 6 sine of negative 5 pi over 6, which again is, if you'd like, 6 sine of 7 pi over 6, which is, again, look up the unit circle if you have to, it's not a big deal, and you'd see that this is negative 1/2, right? Am I mistaken? Yes, this is negative 1/2. So this is proof I don't have the unit circle memorized right there, that this is negative 3. And so the point 6, negative 5 pi over 6 in Cartesian coordinates is the point xy equals negative 3 root 3, comma, negative 3. And here's our conversion. Okay. And so there's an example of being able to go from polar to Cartesian. And in homework and in the recitation, we'll make sure that we get very comfortable going back and forth between the two. And I would strongly recommend, as you do this, even if the question doesn't require it, it does not take much extra work to plot these points and make sure that they do indeed line up. So like we learned that this is negative 3 root 3, comma, negative 3, right? And plotting points for polar coordinates will be very beneficial to you if you learn it now, because in the next video, we're going to learn about functions in polar coordinates or polar curves. And once we start trying to learn about how certain functions behave in certain ways, we need to get an idea of what these graphs look like. And the way we do that is just by plotting points and then connecting the dots. So I would strongly suggest when you're going through problems, converting to and from polar and rectangular coordinates, plot the points. So that's like maybe my best advice here. Advice would be to draw pictures. I would always have a graph, you know, in some point somewhere where the x and y are specified, and then look at the r theta and make sure that you understand why this point belongs where it does in terms of polar coordinates. All right, so that'll wrap it up for this video. And then in the next video, we'll take a look at polar curves and a handful of types of functions in polar equations. And then after that, in the next lecture, like in the video beyond the next video, we'll start to look about at like integration and more calculus, but now in polar coordinates. So like arc length and area. So I'll see you guys in those videos.